Good afternoon. Wear your mask, please. That will be my first instruction. I shouldn't say, but please do that. My name is Johan Knapen. I'm from the IAC in Tenerife. And I must say it's pretty scary to be up here. This is a big room, and after seeing Zoom screens for 2 years, this is great. I'm very glad to be chairing this session this afternoon, or the first part of this session, among others for two reasons. One is that we're in Valencia, and I'm partly responsible for the fact that we are here. I think we started discussing this back in 2018 or so with people like Vicente Martinez. He hasn't been named much. I don't know if he's in the room. But there's been years of discussion, hard work, and it's very good to see you finally back in Spain and in Valencia at this meeting. And the second reason is that the MERAC session at the EAS, or previously EWAS meetings, really is, I think, my favorite session of the whole week, because it's fantastic to see prizes awarded always, but especially the MERAC Prizes, which are awarded to young people, and they're actually substantial prizes. So I'm very glad to introduce to you, to present this year's prizes, Professor Lucio Mayer, who is the director of the Institute for Computational Science at the University of Zurich in Switzerland, and he is also a member of the board of the MERAC Foundation. So, please.
Thank you very much. It's a pleasure to be here finally in person, to be able to introduce and award the prizes. I've been involved in MERAC in the last 4 years, but this is the first year that I'm actually here in person to deliver the prizes. I wanted to remind everyone that the Merac Foundation is really proud to have this role in supporting young scientists in Europe. The prizes that the Merac Foundation awards are quite substantial, because in addition to the main prize, which is 25,000 euros per each of the prizes, there is a project grant, which starts at 50,000 K, which really serves as a seed funding for the early career scientists. So this is something unique. I think there's no other opportunity like this offered at a European level, and especially not anyone that is linked with the European Astronomical Society. So I think I am happy to be here to represent the foundation. Karl Stadelhofer, the president, and Jean-Marie Louzier, who is the third member of the board, could not be here, unfortunately, but they are also very proud, and they are extremely committed to keep supporting scientists for the next decades, whenever it will continue to be so. And next year will be a special year because it will be the 10th year after the MERAC Prizes have begun. The first one was awarded in 2013, so we hope to have a special celebration for that. And I think with this, I'm happy to introduce with Johan the prize winners. So we will start with the first prize, which is the Best Theory Prize. And I think we can... Please. So it's a pleasure to award the PhD prize in Theoretical Astrophysics for 2022 to Helmer Koppelman. Elmer did his PhD at the University of Groningen, a Kaplan Institute, in 2021. And he deserves the prizes for his multifaceted approach to the field of galactic archaeology that transformed our understanding of the history and dynamics of the Milky Way. And without further ado, I let Helmer begin his talk.
Hello. Hi, everyone. I'm super excited and honored to be here today, and I would like to thank the EAS and the organizing committee for giving me this opportunity. And I would like to thank the Merac Foundation for awarding me this prize. And before I get started, I have a small notice, which is that I sadly left academia about half a year ago. And so this means a couple of things. So firstly, this week is my vacation, and I've been having a lovely but very unique vacation. But more importantly, even though I tried to update my talk as much as possible, it might be the case that I've missed some recent updates. And lastly, my talk might be a little bit less scientific and a little bit more storytelling than some of the other talks at this conference. And the story will be about the formation history of the galactic stellar halo. And firstly, I'll explain why the Milky Way is so interesting to study, because this is a question that I get asked very often. And so people always ask me, why out of all of the galaxies, why is the Milky Way so interesting to you? And the reason I would say is that the Milky Way is special because it's not very special at all. It's a spiral galaxy, just like 2 out of 3 other galaxies. And compared to other spiral galaxies, it's pretty average in mass and size. However, of course, compared to all other galaxies, it's by far the most nearby galaxy to study. And it's the only one that we can study from within, and we can study by looking at individual stars. And so by studying its history, we can then learn something about the history of an average spiral galaxy. But of course, you should keep in mind that the Milky Way is just one example of the formation of a spiral. And it's certainly not a representative subset of all of the spiral galaxies. Okay, so what does galaxy formation look like? So the most favored theory at the moment is that galaxies form hierarchically. And so that means that they start off small and then merge together and grow bigger. And this formation channel accounts for about half of the mass of the Milky Way. And the other half comes from continuous accretion of dark matter and gas from the intergalactic medium. However, for today, we'll just focus about the mergers, so the merger history of the Milky Way, and we'll forget about this continuous accretion of material. And here's an example of what such a merger looks like. Here we see a cartoon or an illustration of the Sagittarius dwarf galaxy merging with the Milky Way. And in the first panel, we see that the dwarf is approaching the Milky Way, but nothing's happening yet. But then in the second panel, you see that once the dwarf gets very nearby the Milky Way, the internal tidal forces of the dwarf galaxy start to battle and lose to the external tidal forces of the Milky Way. And this causes stars being stripped from the body of the dwarf galaxy. And in the illustration, you can see that this happens in one direction, the trailing arm, but usually there's 2 arms being created, a leading and a trailing arm. And you can kind of see this in the last panel. So let's go to the last panel. So here you see the dwarf galaxy, which is still, there's a bit left of the dwarf, but a lot of stars have been pulled out of the dwarf into these arms. And we call these arms streams. And here you can also see my reason for focusing on the halo of the Milky Way, and that's because these streams are mainly located in the halo of the Milky Way, and not so much in the Milky Way itself. So the subfield studying the history of the Milky Way is called galactic archaeology. And in galactic archaeology, we have our own set of fossils, the galactic fossils, which are halo stars. We call them fossils because they're old. They're typically older than 10 gigayears. And also, they're extragalactic. And so by studying them, we can tell something about the history of our own galaxy. However, just as with regular archaeology, if you want to study the building blocks of the Milky Way, there will always be details about these building blocks that have been forever lost in time. And so the question is, okay, how many details can we still uncover and what is lost? And so the typical scenarios one might consider is, for example, here as in scenario A, did the Milky Way form by merging with 3 relatively large galaxies, systems, or was it more like scenario B, where there was a wide variety of merging objects? And so typical questions to ask are, how many mergers did the Milky Way experience? How large were these mergers? Was there a variety of merging objects, or were they all similar? And when did these mergers happen? Was there a short burst of merging, or was there an extended period of merging? And finally, the most interesting question to me, at least, to ask is, to what extent these mergers affected the current structure of the Milky Way? So which components of the Milky Way that we observe today are a direct consequence of perhaps one or maybe more of these mergers? And so the way to answer these questions, or one way, is to look into the Gaia data. If you've missed the sessions earlier this conference on Gaia, a quick summary: Gaia is a satellite in space that is mapping the Milky Way. And by mapping, I mean it's observing the positions of stars on the sky, but also proper motions, distances, and photomic information like magnitudes. And for a subset, it's also measuring the line of sight velocity and some other spectroscopic observables. And such a map is beautiful for a scientist like me who is interested in studying the Milky Way. However, there's one issue, and that is that typically the the quality of the data decreases with distance. And so if you select a high-quality subsample of the data, you're left with a relatively local volume of stars. And I say relatively local because the radius is still a few kiloparsecs. And you can see here in this diagram that in the image that this volume is located at the position of the sun roughly, and that's because that's where the satellite is, of course. And so when we go back to these streams, these remnants of mergers, and let's hypothesize that Gaia is located here, and its red circle here is this high-quality subsample, then you will immediately understand that it's impossible to see the entire stream. You only find a local part of this large structure. However, the good thing is that actually detecting this local part is relatively simple, and that's just by focusing on stars that are moving in one single direction. But the complexity also is that for this stream in this location, so let's say Gaia is now located here, then the streams tend to overlap themselves. And this is a simple, good-looking example, but for old streams and long streams, especially those formed by large objects, this can happen 100 times maybe. And so in this case, you would find locally two separate streams, two disconnected streams that seem to be moving in opposite directions. And you wouldn't be able to tell purely by looking at the velocities that these streams belong to the same global large structure. And so the way to disentangle this is by looking not only at kinematics, so the directions in which stars move, but also to look at the dynamics, which are the trajectories of the stars in the Milky Way. And so firstly, here in the bottom left diagram, we're seeing the velocity space of this particular location. And you can see that there are two groups of stars, one moving towards the left and one moving towards the right. Whereas in this case, this is all the same stream. And then in the other diagram, we're looking at a representation of orbits. So you can calculate an orbit of a star by taking a model for the Milky Way. And usually we use relatively simple models that are nice and symmetric. And for these models, you can then calculate a trajectory or an orbit by taking the position and velocity of a star. And so orbits, typically in symmetric models for the Milky Way, can be characterized by a couple of constants. We call them the integrals of motion. And these are values or properties that you can calculate at every location of the trajectory, and which are always the same. And so examples of these are the orbital energy and one component of the angular momentum. And so you see, if we take these same stars, so in the two separate local streams, and map them to orbit space, they're all clumped together. So this is a very powerful tool in looking for streams in the halo of the Milky Way. And to give you an idea or a feeling of what this might look like if there are multiple objects in a halo, here we're looking at a simulation of 30 dwarf galaxies that have merged with the Milky Way, or at least with the Milky Way analog. And it's a very idealized case, scenario, and so the data might not look like this, but this is just to give you an idea of what it might look like. And so you can see that each individual dwarf galaxy, in this case, is located at a distinct location in this space. And so you might imagine that, okay, if the data were to look like this, then you start selecting these stars and investigate whether they belong to an individual, one object, or multiple. And so this is the way forward. We start looking by velocities of stars, and then also combine the velocities with orbital information. And so here we see data from Gaia. And I'll walk you through the diagram. So it's a diagram of velocities. And so the coordinate system is shown in the illustration on the right. And the individual dots show individual stars in the halo. And so this is a local volume, and I emphasize local, so it has a radius of 1 kiloparsec. And the disk, stars on the disk are shown in this heat map, the orange heat map. And that's because there are simply too many stars locally in the disk to show individually. However, the good thing about the disk is, and we're not interested for the study in the disk, we mainly want to target the halo. But the good thing about the disk is that stars in the disk are all moving in the disk. So in case of the coordinate system here in the phi direction. And so it's relatively simple to remove stars that are part of the disk. And that's by drawing this blue line here and cutting away all of the stars that are inside the blue line. And so what's left are most likely halo stars. And if you remember the previous slide, so what we're looking for were these small groups of stars that were moving in a particular direction. But as you can see from the data, it doesn't quite look like that. Maybe on the left of the diagram, there are a couple of these small groups. And so, because this is a three-dimensional space, you can rotate it and look at it from different angles. And so we found these 5 small groups of stars that we think originate in mergers of dwarf galaxies. However, as you might have noticed, most of the stars in the local halo belong to this one large blob of stars, so this one large stream in the halo. And so immediately the question arose, where do these stars come from? And so the hope was, okay, maybe if we calculate the orbits and look at the energy and angular momentum, the picture looks different, but unfortunately it doesn't. So you can see that these small groups of stars, they're all still clustered together and maybe a little bit more compactly. But however, this large group of stars in this orange box here is still there. And it does not look like it has fallen apart in smaller clusters. And so to go further, to go beyond this, we need more than just kinematics and dynamics. This is as far as the dynamics leads us. And for the next bits of insights, we need more information. And this information comes from the galactic DNA or the chemical compositions of stars. And if you're unfamiliar with looking at chemical compositions of stars, so ironically, even though the periodic table contains so many elements, a person like me is usually interested in about 3 elements. In this case, on the horizontal axis, we're seeing the logarithmic ratio of iron versus hydrogen. And on the vertical axis, we're seeing the logarithmic ratio of magnesium to iron. And what's shown here are individual stars, and they're color-coded by in which location or in which dwarf galaxy they're currently located. And so these are all surviving dwarf galaxies that are orbiting the Milky Way. And in the background, in gray, we see stars that are part of the Milky Way itself. And so the first thing to notice from this diagram is that stars with the same color are all located in the same location. So stars that are born in the same system tend to cluster together. So apparently, from the chemical compositions, we can tell something about in which system these stars are born. And not only can we tell something about in which system they're born, we can also tell something about the properties of that system. And that is that the systems tend to order by their sizes. And so stars formed in the smallest system, in this case the Sculptor dwarf galaxy, tend to be located towards the left of the diagram, and stars formed in the largest system, in this case the Milky Way, tend to be located mostly towards the right. And so by studying the footprint of the stars in the space, we can tell something about the size of the system in which they were born. And you might have noticed also, and this is especially evident for the Milky Way, that there's a characteristic footprint that's kind of from left to right, first horizontal, and then sloping downward. And this footprint is created by the different supernova types that are chemically enriching the galaxy. And so as you know, galaxies, when they start forming their first stars, they're very metal deficient, because after the Big Bang, there aren't many metals around, if any at all. And so all galaxies start towards the left of the diagram, and then the first supernova that explode and chemically enrich the galaxy drive a more or less horizontal evolution. But after about 1 gigayear after the first stars form, the different kind of, the new type of supernova, in this case the 1A, start to also explode and kick in and drive a more vertical evolution in this diagram. And so this creates a, well, not a unique, but at least a distinct footprint in this diagram. All right, so let's take this and apply this to the local halo of the Milky Way. Because remember, we were interested in studying this large blob of stars that seem to be part of one large stream in the halo. So what could this be? And in the diagram on the right now, we see the same stars. So the stars in this orange box are color-coded orange, and the stars in white are now individual stars in the Milky Way. And the chemical diagram is the same as, or the similar one as the one before in the previous slide. And you can see here, the first thing to notice is that the stars in orange are significantly different from the stars in the Milky Way. And so this means that they were formed in a separate system. So they're extragalactic. And the system then merged the Milky Way, which is why we find the stars in the Milky Way today. And not only can we tell that they were formed outside of the Milky Way, also, as I was explaining in the previous slide, we can tell something about the size of the system in which they were born. And in this case, because the stars in orange are towards the left of the diagram relative to the Milky Way, that means that they were born in a smaller system. And by taking a model to explain this characteristic footprint of horizontal versus more vertical evolution, we can also put a rough estimate on the mass of the system in which these stars are born. And so it turns out that the stars in orange are all consistent with being formed in a gigantic dwarf galaxy with a stellar mass of 6 × 10⁸ solar masses. And so for us, this was evidence enough to say that all of these stars were formed in a large dwarf galaxy that a long, long time ago merged the Milky Way and is no longer around. And so we named this dwarf galaxy Gaia Enceladus. And there's another interesting part of insight, and it comes from looking at the stellar ages of the stars in Gaia Enceladus. And that's because when a dwarf galaxy merges with the Milky Way, it stops forming stars. And so by looking at the youngest star that you can find in a stream, you can tell something about the time of the merger. And in the case for Gaia Enceladus, the youngest star is about 10 gigayears old. And so this puts a constraint on the time of the merger, which most likely was around 10 gigayears ago. And even more interesting, if you then compare the ages of the stars in Gaia Enceladus to the ages of the stars in the Milky Way's disk, you will see that the youngest star in Gaia Enceladus is younger than the oldest star in the thick disk of the Milky Way. And so this means that the thick disk of the Milky Way must have been in place at the time of the merger. And so this led us to believe that the merger, so this Gaia Enceladus that merged with the Milky Way, was so massive that it really shook up the Milky Way and, at least in parts, created the thick disk. And so it has forever altered the structure of the Milky Way. And so this was the story of Gaia Enceladus, the majority of the local halo, and I emphasize the local halo. And afterwards, we started looking into these smaller streams. And I won't go into details, but these also belong to individual dwarf galaxies that merge with the Milky Way. And I just wanted to show today that this is a very active field of research in which even last month papers are still appearing on the archive, studying these streams and objects in various ways, from dynamics to chemistry and ages. And there are 3 developments in the field that I wanted to highlight. So the first one being the one shown here, which is the study to not only look into dwarf galaxies that have merged with the Milky Way, but also look at globular clusters that came in together with these dwarfs. Because as you can imagine, a dwarf galaxy can have its own system of globular clusters. And so if that dwarf and globular cluster system then merges with the Milky Way, something must happen to these globular clusters. And so either they are still surviving and part of the globular cluster system of the Milky Way, or the globular clusters disrupted and formed their own streams, which are known as thin, cold streams. And in the diagram here, we're seeing again this orbital space, so the energy and angular momentum. And the colored dots are individual cold streams. And so what people started to do is look into to which dwarf galaxies these streams belong. So when did they come into the Milky Way, and to which object did they belong initially? And the second development that I wanted to highlight is one where we stepped away from using manual selection boxes and polygons to select stars that belong to mergers, and to use clustering algorithms and machine learning to more statistically robust tell and extract individual mergers from the data. And the final development that I wanted to highlight is one where people started to go beyond the data from Gaia and to complement the Gaia data by targeting halo stars that are a little bit further out. Because as I was saying before, most of the analysis that I've been showing has been based on a relatively local volume of the halo. And so you can imagine that a little bit further out in the halo of the Milky Way, we will find other objects that have also merged with the Milky Way, perhaps a little bit less long ago. And so these are my takeaway points. I'll thank you again for your time and attention. I'll leave them up on the screen, and I think this is the perfect time for some questions.
Thank you very much, Helmer. Fantastic talk. And you were actually well on time, so we have time for questions. Questions, comments, anyone? It's hard to see from here, but there is a question. Yes, go ahead, please.
Thank you very much. Indeed, very good storytelling and nothing wrong with doing a little bit storytelling. I have a question for you. So we can imagine that some of the systems that accreted with Milky Way accreted something smaller on their own before being accreted by us, like, the biggest fish in the ocean end up at the end of the chain. Is it possible to that some of this archaeology you have, so like one stream would actually have a different mentality because it will coming from one object that merged with Milky Way, but actually it had some of its own previous different components. Can your method actually be pushed to try to detect things like that?
Yeah, it's a very good question. And it's one that we haven't considered so far, as I'm aware, and it really complicates the story. And actually, it's very relevant because at the moment, we're kind of merging with the Large Magellanic Cloud and the Small Magellanic Cloud, and so it's a double system. And so this most likely has occurred before, and it will be complicated to disentangle. And to add on to this, there's another complication, and that is that especially large systems tend to have a metallicity gradient. And so meaning that the core of the system is chemically different from its outer rings. And so this means that also the stars in the dwarf galaxies do not all have the same chemistry. And so it might look like, as if in the diagram, there are two separate components which actually belong to the same system. And yeah, that's just to say that this field isn't finishing anytime soon.
Good, thank you. There is time for another question or comment. Anyone? Wave wildly so we can see you if there is anyone. There's someone waving wildly. Go ahead, please.
Yeah, following up on your question, sorry, your comment, I was curious how far in principle can we push that into the past, because of course these kinematic signatures get wiped out by the various relaxation processes, and chemical signatures might not be distinct enough. So how far, can we help to detect 10 mergers, 100 mergers in the past? What's your opinion on that?
Yeah, that's difficult to answer because I honestly don't know the answer to this. But I think it's promising because the systems that are merging right now, or as have merged a little bit longer ago, are, yes, so the more recent mergers tend to be located in the outskirts of the halo. And so in the insides, we tend to have the older systems. And I think because of this, you can go back quite far, so up to 10 gig years, maybe a little bit further, but I'm not sure.
Thank you. And with that, we should thank Helmer again for his talk, but also especially congratulate him for his prize. Thank you. And we move on to the presentation of the second prize. And again, Lucio Mayer will take the honors.
It's a pleasure to present the second winner of the Merac Prize for the best PhD thesis of this year for the Observational Astrophysics category. This is Núria Miret Roig, who got her PhD in 2020 at the University of Bordeaux. And she gets the prize for the discovery of many new free-floating planets, which illuminated the origin of these exotic nomad planets. Thanks a lot.
Keep moving, keep going, keep going.
So, thank you very much. I'm really honored to have received this prize. So, I think it's always very rewarding to have your work recognized, but I think this is a very special prize because it gives me the opportunity to talk to you all and to get to know the work I have been doing so far. And also because we have learned that part of the prize is to help us early researchers to continue pursuing this career. So I hope to be able to take this chance, and I hope this will help me to continue in research for more years. So for that, I would really like to thank the European Astronomical Society and the Merac Foundation. Then I also wanted to share with you that, so this is the first time that I give a talk in a professional conference. So for that, I would also like to thank the European Astronomical Society for having prepared this in-person conference, because I think, at least to me, it was a great chance to meet you all and also to have the opportunity to talk to some of you during the coffee breaks. So I really take new ideas home, and this really helped me to push my research forward. And finally, last but not least, I would like to thank all my collaborators who participated in the research that I will be presenting today. So those are the ones listed here. I'm really grateful to all of them, because without them, I would never have got to the results that I will be presenting today. And I would like to especially highlight the role of Hervé Bouy and Javier Olivares, who were my PhD advisors, and I'm really, really grateful to them. So with this short introduction, so now I will start by presenting the work that I did and led me to get this award. So I would like to start by mentioning 3 of the key points that I would like to discuss with you today. So first of all, I would like to present the idea that free-floating planets are a common output of star formation. Then I will discuss the initial mass function as an excellent tool to study the origin of all these free-floating planets. And towards the end, I would also like to mention how we really need to have precise stellar ages to better understand the process of star formation. So let me start by beginning explaining what are these free-floating planets and why do we care about them. So free-floating planets are basically the lightest products of star formation. Those are very small objects of less than 13 times the mass of Jupiter, and they are very particular in the sense that they are not part of any planetary system. So they are, instead, they are roaming among the rest of stars in our galaxy. They are so light that they are highly sensitive to dynamical interactions, and this makes them very interesting to better study the initial conditions in star-forming regions. The first free-floating planets were discovered more than 20 years ago, but still in the present we are missing large samples which allow us to study their characteristics, their properties, and also their formation mechanism. And the reason is that they are extremely faint, extremely challenging to detect, and only in very nearby regions and when they are very young, we can actually detect them directly by direct imaging. So we know that these free-floating planets can be formed by different mechanisms. For instance, they can form similarly to low-mass stars when small clumps of gas become gravitationally unstable and collapse. Then also they can be formed in planetary systems like usual regular exoplanets, and then due to dynamical interactions in these planetary systems with other exoplanets or the disk itself, so one of these planets can eventually become gravitationally unstable and abandon their birth system. And this will become eventually a free-floating planet. Also, we can think of a scenario where several cores are accreting mass from the same gas reservoir. Also, due to dynamical interactions, some of these cores can eventually be ejected, and they will not be able to accrete enough mass to become a star, and those will become also planetary mass objects. And finally, also at the vicinity of very hot massive stars, the strong stellar winds of these OB stars can evaporate the outer layers of an accreting core, which will not make it to a star either. So we know that all these mechanisms, in principle, can form free-floating planets, but currently there is still a debate of which is the most important mechanism, or which are the relative contributions of all these mechanisms in producing the final sample of free-floating planets that we have. And this is one of the questions I addressed during my PhD. And to try to answer these questions, I used what we call the initial mass function. So the mass function basically is the mass distribution of stars right after a starburst. So basically it tells us how many types of stars form at each time. For instance, we know that OB stars, very massive stars, are very rare, while low mass stars are the most common output in star formation. And what's still difficult to measure to date is the content of substellar objects, that's to say of brown dwarfs and planets. Here we are seeing another representation of the mass distribution, and here I would like to comment the fact that currently, thanks to the Gaia satellite, it's relatively easy to select groups of stars which are moving together in the space and therefore which were formed together, and this allows to relatively easy study the stellar content of the mass function. However, if we want to also detect the lightest objects that form with these stars, most of them are still too faint for Gaia and are beyond the Gaia detection limit. And this is why we need images on the ground to complement for Gaia. And this becomes even more important when we look into very young star-forming regions, because those regions are still embedded in their parent molecular clouds. And then Gaia, which operates in the optical, is mainly blind to these very embedded sources. And from the ground, we can complement Gaia with infrared sources, with infrared images, and detect these lightest objects. And this was exactly the idea of the Cosmic Tents project, which is an ERC project by Hervé Bouy, and also the goal of my PhD. So basically what we did is we tried to provide catalogs of nearby star-forming regions to later identify the members, paying a special attention to the less massive ones, to later on study how these stars and planets formed. Now, let me introduce the region where I devoted most of the time of my PhD. So here you are seeing an image of a 170 degrees square region in the sky. And towards the center, we see the area of Eucus, where you can see that there is a lot of gas and dust, because stars are still forming here. So these are very young, but then also very highly complicated to detect because of this gas and dust. At the same time, very nearby, we have the OB association of Ophiuchus, which is slightly older, but where the majority of gas and dust has already evaporating, facilitating a lot the identification of young stars. So we wanted to focus in this region, and the first thing we did is to try to map this region with ground-based images. And for that, we carried on our own observations, and this gave me the opportunity to visit some of the most amazing telescopes that we have on Earth. And we complemented these images with all public images in archive. And by doing this procedure, we were able to compile around 74,000 images taken over the past 20 years. This 20 years time span is very important, because we will not only be interested in positions and photometry, but also on the proper motions, and the wider the time span, the more precise the proper motions will be. So here, just to comment on the complexity of this analysis, you can see that these images come from many different instruments with different pipelines, and also the amount of data that we had to analyze is really, really huge. So when we combined all these images, eventually we produced what we call the dance catalog, which contains positions, proper motions, and multiband photometry in the optical and in the infrared for 26 million sources. This catalog was complemented with Gaia, where we took all the Gaia sources also in this region. And really, Hipparcos was only used because the most bright stars, like Antares, they are too bright for Gaia. And for the sake of completeness, then we only used Hipparcos. We also used Hipparcos. But the main analysis was done only with Gaia and DENS. And what I'm showing here is a comparison of the proper motion uncertainty as a function of magnitude. And really, the point here is that Gaia is doing an amazing job for bright stars. For sure, this is the best proper motions that we can think of. And really, the importance of our ground-based image comes towards the faintest objects, where we can still measure the proper motion with a relatively good precision for sources 6 magnitudes deeper than Gaia. And so what you are seeing now is one of the images in this region of Upper Scorpius and Ophiuchus. So you can see in this image many stars, also a few galaxies, which are these reddish elongated objects. And so now I would like to, I have a question for you all. And it is whether you can try to guess which is the object that is exactly at the center of this image. The center is around here. I don't know, maybe at the background you cannot really see well, so then you can just look this image on your computer. This is an image we prepare for a press release to accompany our work. But yeah, so the center is around here, and basically what we should be seeing is one of the free-floating planets that we identified. So I find really excited that we not only were able to observe this tiny little red dot in our images, but also we could measure how this object moves in the sky during different years. So we could measure the precisions with the proper motions with a precision enough to detect this free-floating planet as co-moving with all the rest of objects in this region. I would like to discuss very briefly, without getting into details, how we do to select all these free-floating planets and the rest of its family. So basically, we use a semi-automatic methodology developed by Luis Mazarro and Javier Olivares, which is especially designed to work with this huge with these huge files of very many sources. And the idea of this methodology is that we can combine all the information that is available, so we can combine proper motions and photometry together with the uncertainties to finally obtain a membership probability for all the sources in the catalog. And with this, we can select the highest probability members of the cluster. And this is exactly what we did. And applying this methodology to the data I presented before, we were able to identify 3,500 members of this region. And from those, between 70 and 170 of which are free-floating planets. And those are the circles that you can see, the red circles that you can see in this image. And it's interesting to see that they cover more or less all the region that we analyzed. So most of them are in the region of Upper Scorpius, but also some of them are in the region of Ophiuchus. A very important thing to mention is that we have very recently also carried a spectroscopic campaign to validate our membership analysis, and we observed with spectra some of the coolest members in our sample, and we were able to validate 16 and to confirm 16 targets as young ultra-cool dwarfs. This means that our survey has a success rate of around 95%. So, and this validates a lot all the conclusions that I will be showing in the following slides. Also, I think that these targets are going to be excellent targets for the James Webb Space Telescope. So we have been hearing a lot of great things about James Webb in this conference, and I think those targets are going to be great to maybe to study the atmospheres of these planetary mass objects, which will not be affected by a bright star which is nearby. And in any case, they will also be very interesting to compare with the atmospheres of regular exoplanets, and this will certainly bring us a lot of new information on the origin of these free-floating planets. So then another thing we did is we took all this family of stars and planets that were born together, and we built the magnitude distribution. So the magnitude distribution, which you are seeing here, is a direct product of observations, and therefore it's a direct product of observations, and thanks to the large number statistics in our sample, we can see that this magnitude distribution has very low uncertainties. And therefore, we can see all kinds of details in this magnitude distribution. For instance, I would like to call your attention to this dip that we observe at planetary masses. And this is not the first time that this dip is observed, but I think this is one of the first times that we observe with such a statistical significance, and which validates the fact that this dip is there, and we have to understand now which is its origin. So it has been suggested that this dip could mean that several formation mechanisms are playing a role at these planetary mass objects, and I agree with these ideas. And now our work is to try to understand which are the important mechanisms playing a role and which is their contribution. Very briefly, so a similar dip has also been observed recently by Gaia in a 100-parsec bubble. However, whilst this sample contains only young objects, this dip in Gaia contains both young and old objects, so it's still to be checked whether this dip has the same origin or not. But for sure, this will be also an interesting thing to investigate further. And now I would like to go towards the end and to present the mass function that we obtain in this region. But before, I would like to say also a word of caution, because obtaining stellar masses is highly complicated. Basically, the masses is not unobservable, so we have to rely on evolutionary models to convert luminosities to masses. And evolutionary models especially change a lot at very early stages. For instance, here you can see the isochron at 1 and 10 million years, and already with this short time difference, an ultra-cool object can have cooled down up to 4 magnitudes. So this, for sure, if we don't know precisely the age of our objects, this will introduce a source of uncertainty in the final mass function. But not only this, also we know that evolutionary models are especially uncertain at very young ages and for very low mass stars. Part of these uncertainties is because we don't have many samples where to test our objects, so I hope that this sample will be able also to contribute as a benchmark sample where to test and improve models here. But in any case, so we took these evolutionary models and we then converted and computed our mass distribution. So here at the top, you are seeing the magnitude distribution that we have already discussed, and at the bottom, you see the mass function. And in this mass function, first we can look towards the high mass end, where this is compatible with a Salpeter slope, similar to what many other works have found. And it's also interesting to comment the low mass end of this mass function, where we believe that the fraction that we report is only a lower limit of the true value of free-floating planets in this region. The reason is that first, we have proven that we have a very low contamination rate in this sample, thanks to spectroscopic observations. And also, we believe that we might be missing some of the most embedded objects in this region. So in fact, the true value could be even higher. Okay, so now I promised that I wanted to discuss which is the origin of all these free-floating planets. And for that, what we did is comparing the mass function that we obtained from our observations to what numerical simulations have found. And in this figure, you are seeing that this red line indicates our observations, whilst the white line corresponds to numerical simulations where they form stars and planets mainly by core collapse formation. Then, comparing our observations to the predictions of these models, we found that probably at least 13% of the free-floating planets that we found are formed by this core collapse mechanism. But it's looking into this figure also, it's quite noticeable that the fraction of free-floating planets that we observe is way higher than the predictions of this model. So what is indeed the origin of all these free-floating planets? Then, to try to answer this question, we considered another mechanism I was introducing at the beginning, and it is ejection from planetary systems, right? So we believe that a fraction of these objects could have formed in planetary systems and later abandoned their birth site. So basically, by comparing the fraction of free-floating planets in our observations to observations of other exoplanetary systems and models which predict this, the ejection of these exoplanets, we could estimate that probably around 10% of the free-floating planets in our sample were formed in planetary systems. Then I would like to stop a second here because I really think that the main result and the main contribution of our work is not really the final values that I am showing in this slide. Those are affected by a lot of uncertainties, both from the models and from the observations. But I really think that what these results are telling us is that these both mechanisms at least are taking an important role in forming free-floating planets, and we need more effort both from the observational side and people doing numerical simulations to continue to investigate the origin of these free-floating planets. And before finishing, so this is mainly what I have presented so far are the results of my PhD, but now I moved to the University of Vienna when I'm pursuing my postdoc, and now I would like to move to study the kinematics of this region. So several authors have already shown that the kinematics of this region is very rich, and there are probably several populations coexisting in this region of Upper Scorpius, and probably the age of these populations have a slightly different age. So identifying these populations and measuring their age precisely is crucial, not only to improve the mass function that I was showing, but also to try to unravel the star formation history of this region and to address questions like where did the star formation begin in this region and how it propagated to the rest of the region. So hopefully these are questions I will be addressing in the coming years. And with this, I will just leave you with my summary. And I'm really looking forward to discussing all this work I presented today, either now with questions or afterwards in more private situation. So thank you very much to all of you for your attention. And yeah, I'm looking forward to discussing with you.
Thank you very much. That was fantastic. I have a very small first question. Did you say this was your first talk?
Yes. Well, in a in-person conference, yes.
I think you deserve another applause just for that.
Thank you.
That was very impressive. Any questions? There's one there. Yes, go ahead, please. State your name, please, before you ask your question.
Hans Zinnecker. Hello.
Hello.
Well, we also proposed a mechanism for free-floating brown dwarfs by erosion of cores by massive stars, by the ultraviolet radiation. But maybe that process is not so important. Your process might be more important. But I wanted to point out yet another process that might be important here, and you touched upon it, but not enough. And that is most of the stars, low-mass stars, form in binary systems. So if you have planetary systems in binary systems, there will be a huge probability of ejection. You know, and not only, and this goes further than what you have said, not only will the sub-Jupiter or the Jupiter-sized planets be ejected, but also the Earth-sized planets. And that, to detect those, you need other methods, namely gravitational microlensing. And so this is a wonderful subject, but it's even vaster than you had indicated. But congratulations, a great work.
Yeah, so absolutely, I completely agree with you. In fact, I didn't mention it, but the least massive objects that we detect, they are around 4 times the mass of Jupiter. So absolutely, with the current capabilities that we have now, we cannot go towards least massive objects. But in fact, we believe that there must be even many more, because exactly what you were saying, right? Even the least massive objects are even more likely to be ejected. So probably there are even more Earth-like free-floating Earth in this region. But yeah, so we could not detect it with these techniques, but for sure it would be interesting to try with other techniques. Yeah.
Lex Kaper, thank you for this beautiful talk. If I would have been the first person to ask a question, I would have asked whether Hans Zinnecker would be in the audience to ask you about the binaries. But I have a slightly different angle. We actually looked at the upper Scorpius and the binaries and the binary companion mass function. And there actually you see something very interesting. That is that the mass function of the binary companions is, as you have shown in a sense, an extrapolation from the high mass end to the low mass end. But then you actually see an upturn if you come to the planetary companions. And that is not so much what you saw, but what may be very interesting, because from binaries you can get actually masses, is to see whether you can connect these two observations, your free-floating planets and what has been mentioned by yourself, and perhaps also look at the binary companion mass function.
Okay, thank you. I will look into this.
We have time for another comment or question. If anybody waving at the back in the middle there.
Did I read your graph correctly that the dip at around 10 Jupiter masses disappears when you go from the luminosity function to the mass function?
Okay, so this is a great question. In fact, I didn't have much time to discuss it, but since you're asking, so it's true, we observe it in luminosity function, but not in the mass function. But we are not sure whether this means that this is a feature only that we would only observe at the luminosity function, or whether this is hindered by the uncertainties we have in the mass function. Because in the mass function, we inherited all the uncertainties with evolutionary models, and also the fact that we don't know precisely the age, because I have briefly discussed at the end that there are probably several populations. So the error bars in the mass function increase a lot compared to the magnitude distribution. So I think with the current data that we have, I wouldn't dare to say whether this feature is not there or we are not seeing it yet.
So you don't see something in the mass luminosity relation at a given age that would explain that would naturally explain the dip?
Well, let me go. So here, those are the models that we are using, and you see that they have some kind of features here. I don't know if this could at some point be causing and hiding this dip, or this is for what I was saying, because we are having different populations, and at the moment, when I was showing this mass function here, so what we did here is we assumed a very pessimistic case in which all the stars and planets are 10 million years, so we used the 10 million years isochron to compute the mass function, and then we repeated the exercise in a very optimistic case where we assume that all stars and planets are only 3 million years, and those are the upper and lower limits that you are seeing in this function here. And we believe that the truth must be somewhere in between, but again, so I think that the thickness of the error bar compared to the error bars that we have in the luminosity function don't allow us to say whether this dip is not here or we just don't see it.
What I would like to see ideally is the derivative of the mass to luminosity.
We should move on, sorry.
Yeah, sure.
Yeah, good. No, I just want to let Luia go off and celebrate. Congratulations again. Thank you very much.
Thank you.
And while we move to the presentation of the third award, I just want to share with you an interesting but ultimately irrelevant fact, which is that the nationalities of the three winners of today, in the correct order, correspond to the host nations of last year's EAS meeting, this year's EAS meeting, and next year's EAS meeting. Whether that was by design, no one, I think, will ever know. We move to Lucio again, please.
Thank you. So we come to the last prize to be awarded today. Again, the best PhD thesis, this time for new technologies, in particular for instrumental, is awarded to Ewelina Obrzud, who got her PhD in 2019, working at the University of Geneva, and also at the Centre Suisse for Électronique ou Microtechnique in Neuchâtel, where she is now. And she is awarded the prize for the development of novel laser frequency comms for the accurate calibration and extreme radial velocity precision of astronomical spectrographs. Congratulations, Ewelina.
Thank you very much.
Keep going, keep going, keep going, keep going, keep going, keep going, keep going.
Good afternoon. First of all, I would like to thank the Merac Foundation and EAS for this distinction. I would also like to thank people with whom I work during my PhD and also beyond. First, the Exoplanet group at the Geneva University and the Quantum and Laser Tech group at the Swiss Center for Electronics and Microtechnology. And it's a great pleasure to be here today and to have this opportunity to talk to you about the subject of my work, which is laser frequency comb. In other words, optical frequency comb, a frequency ruler, or astrocomb if it's used in astronomy. So what are laser frequency combs? Why astronomers are intrigued by them and sometimes not very happy about them? And in this presentation, I would like to give you a big picture of laser frequency combs and tackle some challenges related to their generation. So this is the outline of my presentation. First, I will start with a scientific motivation from the astronomical point of view. Then I will move to wavelength calibration, and then I will discuss astrocombs. What are they? How are they generated? What are the challenges? And then, in the end, I will tackle some ongoing, interesting projects that I'm involved in that will give you a bit of a glimpse into the future of astrocombs. So it all starts here with astronomical spectroscopy. More precisely, it's the extreme precision astronomical spectroscopy. This is a field that deals with objects of various sizes. On the one end, we have the building blocks of the universe, where scientists try to measure the variability or the invariability of fundamental physical constants, seeking new physics or trying just to break the standard model. Then we have the field of exoplanets, their detection and characterization, the field that has been extremely prolific over the recent years. And then if we move up a few orders of magnitude in size, there is this one elusive measurement for now, which is the direct measurement of the acceleration rate of the universe. And scientists ask such questions as, is this constant truly constant? Or where is the Earth 2.0? And how fast is the universe expanding? And if you are such a concerned astronomer and you want to get some questions answered, you choose an astronomical object to observe, you get some time on a telescope that is equipped with a spectrograph, and you start acquiring data. Now, in order to get any relevant information from your spectra, such as what is the wavelength of this feature or how did it behave over the recent 6 months, well, the spectrograph would need to be calibrated. Calibration means that each of the pixels on the detector array would need to have a very precise value of wavelength assigned to it. And this is usually done before and after your observations, when a light source with a known spectrum illuminates the spectrograph and then a few magical algorithms afterwards, well, you get a function of pixel versus wavelength, and then you can start working on your data, and probably you discover that you have plenty more problems. But we will stop at the wavelength calibration now. So there are several ways of calibrating a spectrograph. There are several sources that are routinely used on astronomical spectrographs. There are gas cells that are placed on the path of the observed object, imprinting known spectral features on unknown observed spectra, in such a way providing calibration. However, they offer rather narrow-band calibration, and they can be only used on sources that are relatively bright. Then there are emission lines that had emission lamps that had extreme success, for example, with HARP spectrograph. However, because of the effects of blending and aging of lamps and extremely high dynamic range of the emission lines they provide, the precision has its limits. Then there are some spectrographs that use telluric lines, and there are several groups that are currently working on actively stabilized Fabry-Perot cavities. And there are frequency combs. Now, it has been commonly accepted that laser frequency combs are the devices that can offer the best precision possible. Now, why? Well, to answer this question, first, I would like to discuss what is actually a frequency comb. A laser frequency comb is a light source that generates periodic optical pulses. By the Fourier transform, it corresponds to an optical spectrum that is composed of equidistantly spaced, extremely narrow emission lines, like laser lines. And a laser frequency comb is determined by two parameters. The first one is the repetition rate, which is the line spacing. The second one is the offset frequency. It's essentially a point where a laser frequency comb theoretically starts. And the magical thing about a laser frequency comb is that frequencies of each of the comb line can be extremely precisely determined because of this relation, which relates the optical frequency of a mode to the repetition rate and the offset frequency. And both of these frequencies, the repetition rate and the offset frequencies, they are radio frequencies, which means that they can be measured and stabilized and linked to the definition of a second, what essentially means that a laser frequency comb becomes an absolute source. It is like a ruler, but in a frequency space. And this is the reason why, theoretically, a laser frequency comb is a perfect calibration source. Now, not any laser frequency comb can become an astrocomb. There are several parameters, several criteria that have to be satisfied in order for a frequency comb to be dignified with the title of an astrocomb. The first one is a high repetition rate. The line spacing of an astrocomb has to be wide enough such that a spectrograph can resolve it, but narrow enough such that there are as many calibration lines as possible in order to improve the calibration precision. Now, it's called high repetition rate because, taking into account all the applications of frequency comb, it lies at rather higher end of repetition rates. The second criterion is broadband wavelength coverage. Of course, a calibrator has to cover the full wavelength range of a given spectrograph. Here you have several examples of spectrographs and their wavelength coverage. They go from the visible to the near infrared, spanning at least several hundreds of nanometers. The third criterion is exceptional spectral flatness. In order to get the most information from the spectrum, the intensity over the full spectral coverage has to be as equal as possible. Astronomers accept the variations at the order of 50, 60, 70%, what for you might be a lot. However, for a laser physicist, it is extremely flat. Now, the fourth one is not really a requirement, but it's an extremely useful property to have in a laser frequency comb, which is tunability. It's essentially a possibility to shift the full frequency, the full spectrum of a frequency comb, and this allows thorough characterization of the detector array. Now, of course, this is not a full list of properties that an astrocomb should have. We could add repeatability, robustness, turnkey operation, low maintenance, and so on. However, for this presentation, I decided to divide all these criteria into two categories. So we have a technical category and then more engineering-related category. And in this presentation, I will tackle only the technical part, but I wanted to let you know that there is also more engineering-related criteria that are also important and that have their own challenges. So now that we know what astronomers need, how do we actually get there? So an astrocomb can be divided into three independent parts. We start with an oscillator, an instrument that generates optical pulses. Usually at this point, the spectrum is not broad enough to be useful for spectrograph calibration, so we have to go through some nonlinear medium for spectral broadening. Now at this point, the spectrum is extremely modulated in intensity. So it has to go through an additional stage of amplitude adjustment to in the end provide a very smooth spectrum over the full bandwidth. And already here we can determine two challenges. The first one is generating a laser frequency comb with a high repetition rate and broadband spectrum. And the second challenge is generating a laser frequency comb in the UV and blue spectral band. Now let's go to the first challenge. It is not difficult to generate a laser frequency comb with a high repetition rate. And it is not difficult to generate a laser frequency comb with extremely broad spectrum spanning even several octaves in frequency. Now it is a bit more complicated to generate a laser frequency comb that has both of these properties. And in this part, I would like to discuss a bit what are the technologies that are currently being used to tackle this problem and show you some examples. And for this, I invite you for a very brief astrocomb history lesson. There are currently two technologies that are used at the base of astrocomb generation, and the third one that is a potential future astrocomb. In this plot, I will show you a line spacing, so the repetition rate, of systems that have been deployed or tested on an astronomical spectrograph, or tested in lab with astronomical spectrograph calibration in mind, as a function of the publication year of the results related to the system. And the first system I would like to discuss, it's a technology that was used for the very first astrocomb and subsequently has become the technology that is used the most so far. And this technology is based on filtered mode-locked lasers. So mode-locked lasers are extremely reliable and low noise optical pulse generators. They generate extremely short pulses, which is very useful for broadband frequency comb generation. However, their repetition rate, so the line spacing, is 1 or 2 orders of magnitude too low for an astronomical spectrograph to be resolved. And so in order to use this technology as an astrocomb, what has to be done is that the spectrum has to be filtered spectrally. So there are modes of the frequency comb that have to be suppressed by typically Fabry-Perot cavities, such that the line spacing is kind of synthetically increased. And this complexifies the system enormously and may introduce, in some cases, errors on the calibration. And to counteract this, there have been several groups that started working on different technology, a technology that can provide directly high repetition rate systems. And this technology is based on electro-optic modulation. Now, the repetition rate of electro-optic modulation-based frequency combs falls essentially in the perfect spot for the repetition rates. And huge advantage of this system is the tunability of both the repetition rate and the offset frequency. These frequencies can be tuned in operation, giving a huge flexibility for these systems. However, the optical pulses that are generated with this technology are relatively long, which means that we have to add additional stages of amplification and pulse compression, which also somehow complexifies the system. And there is also the case of noise that has to be taken into account when building such a system. Now, the third technology is based on microresonators. Microresonators are teeny tiny optical cavities that can be, in principle, integrated on a teeny tiny chip. And because of their teeny tiny size, they generate laser frequency combs that have extremely high repetition rate. Now, they have the advantage of being of very low noise, and even greater advantage is the fact that they can directly generate extremely broadband spectra. However, this technology is very fresh, very scientific, and not yet at the technology readiness level that can be right now employed on astronomical spectrographs. Nevertheless, there have already been 2 demonstrations of this technology on an astronomical spectrograph, one of which I had an opportunity to participate in. And this is certainly a technology to keep an eye on if you are interested in frequency combs. And all this to show you that all of these systems, they have their advantages and disadvantages. And when building an astrocomb, you have to deal with the disadvantages of the technology that you chose. And all this because astronomy has extremely specific requirements that you cannot really, that you don't really see in other applications of laser frequency combs. The good news is, however, that there is a lot of development going on in the field. As I have shown you, not only Motlock lasers are currently used on astronomical spectrographs, but also electro-optic frequency combs. And because of this competition of the technologies, there is progress, there is steady progress in the field. And now I would like to tackle the second challenge, which is generation of a frequency comb in the blue and UV spectral region. So far, there is no reliable way of generating a laser frequency comb for astronomical spectrograph calibration in this wavelength range. A usual way of going to the visible wavelength range is to generate a frequency comb in the near infrared and then use a combination of bulk crystal and some specialty optical fibers in order to have a frequency transfer from the near infrared to the visible. However, this method does not work very well for the blue and UV generation because optical fibers, at least the way they are made right now, they do not support very well blue and UV photons. They just burn very quickly. And to fight this, there is a very interesting technology that is currently being developed, which is called photonic integrated circuits. So photonic integrated circuits, in short, PICs, they are millimeter or centimeter scale devices that can combine several photonic functions on one chip. These can be very simple structures like waveguides or optical splitters or gratings, or active devices like lasers, amplifiers, or electro-optic modulators. They are developed from various materials, which gives a lot of choice in terms of optical properties or electro-optic properties or active properties. And they are not only interesting from the point of view of a laser frequency comb generation, but also astronomy in general and other applications like telecom and spectroscopy. The structures that are extremely interesting from the point of view of blue and UV generation are nonlinear integrated waveguides. These are structures that are designed to provide nonlinear properties that allow frequency transfer to a desired wavelength band. And they offer several advantages if we compare them with optical fibers. The first one is the lower optical power requirement, which is a good thing if we generate frequency combs at high repetition rates. They offer access to several spectral bands simultaneously, and they not only provide us this access, but give this access in a broadband way. And I would like to show you an example of a use of such an integrated waveguide. In this experiment, we used an electro-optic pulse generator at 10 gigahertz repetition rate. It generates optical pulses in the near-infrared, and the spectrum you can see in the plot. And now on the way of these optical pulses in the near-infrared, we put a silicon nitride waveguide, and you can see the photograph here of such a waveguide in operation. And there are two things that happen in such a waveguide. The first one is the optical spectrum in the near-infrared broadens. And the second one is that there is frequency transfer from the near-infrared to the visible, a broadband frequency transfer. Now, silicon nitride is not an ideal material to use for the blue and UV generation because of its inefficiency. However, there are other platforms that are much more efficient and much more interesting for this regard. And this leads me to the last part of my talk, which are the ongoing projects. And related to the PICS is the BlueVest project. This project is led by the Geneva University with CSCM, EPFL, and DESI as partners. And the goal of this project is to provide a demonstration of a laser frequency comb generation in the blue and UV for spectrograph calibration. And all this using frequency conversion with PICS from the near-infrared to the desired band. And in the photograph, you can see the platform that we are currently working on. It's called lithium niobate. And on this picture, you can see from the left, my left, you can see optical pulses being delivered with an optical fiber. They are injected into a lithium niobate waveguide. And at the end, we have access to an extremely broadband spectra from the visible to the near-infrared, or even at the limit to the mid-infrared. The waveguide glows green because of the scattering also of the third harmonic. And now within this project, we are working on designing the chips such that they provide the frequency conversion that we want, fabrication of these chips, as well as providing an oscillator that will work in conjunction with this PIC to provide the demonstrator. And now, last but not least, this is a project that I'm extremely excited about. It concerns NIRPs. You might have had an occasion to listen to today's talk of François Bouchy about the very first preliminary results of the NIRPs spectrograph. If not, I will just briefly mention that NIRPs is a near-infrared spectrograph that just right now finished the first round of commissioning on the 3.6 meter telescope in La Silla. It's a younger brother of HARPS. And CSCM was engaged to provide a laser frequency comb for NIRPs calibration. The laser frequency comb will be based on electro-optic modulation. And here I would like to give you a bit of a kind of like a timeline of how the system was developed. So in 2017, we had a very lab-style, very spontaneous setup that we tested on the JANO B spectrograph. It was actually a pretty successful campaign that we had over there, for which I would like to thank the full JANO B team that also made it possible for us to go there. And you can see that the system is very, very lab-like. And then in 2019, we put some efforts to to putting the base of the system into essentially a black box, which you can see here with a banana on the top. And we were very proud of it. And right now it's even better because in 2022, we are able finally to provide a turnkey system for a calibration of a spectrograph. And you have the specification listed here, and the delivery is planned for the end of this year. So to summarize, I gave you just some examples of how astrocoms are currently being built, tackled some challenges. But the most important thing is that in the end what we want is to deliver a black box type system such that you can do your groundbreaking science with and you just don't have to worry about. And with this presentation, I just wanted to give you a glimpse of what is actually inside of the box. Thank you.
Thank you very much. Another fantastic talk. The reason I'm pressing on time is the next chairman in this session has threatened me with horrible things if I don't stick to time. Any questions? Wave wildly, please. There's someone waving.
Hello, what a wonderful talk. I really learned a lot. Thank you for explaining it so clearly. Do you have a comment? I've heard that soliton crystals are being considered or experimented with. Would that be in the waveguide part of the system that you've outlined?
So, yes, soliton crystals, it's something definitely very interesting. They are generated in microresonators, so of course they can be integrated on a PIC. This, as I mentioned, this is not yet a technology that is ready enough to be packaged and to be sent to Chile or La Palma and to be used in a very remote way, because I have worked for several years with microresonators, and it's difficult sometimes. It's a very fresh technology. So the good news is that there's a lot of groups that are working on this technology, and I do not doubt that in several years, maybe 10 years, I don't know, but certainly there will be an opportunity for microresonators to be used on astronomical spectrographs, but certainly not right now.
Thank you.
We can have one more short question if there is one.
Hi, we've got similar problems in radio. How low can you go with this kind of system? Could you reach below a terahertz, or is that too far?
Which terahertz?
1,000 gigahertz.
You are talking about generating a frequency comb with a repetition rate of a terahertz, or to go to terahertz spectrum?
Provide a comb for a central frequency of below a terahertz.
Oola. These are not frequencies that I'm used to work with. So I'm sorry, but I think I would need more time to think about that. But that's a good point, yeah.
Good. I think we should stop there. Congratulations again. Thank you very much. Congratulations to all three Merac Prize winners, and this concludes this part of the plenary session. On time, Professor Kylafis. So I hand over to Nick Kylafis from another southern European island. He will be chair for the rest of this session. Thank you very much.
Thank you, Johan. Hello, I'm Nick Kylafis. I'm looking for Bozena, but yeah, please come up. I'm Nick Kylafis from the University of Crete, and I'm extremely happy to present this year's Lodewijk Woltjer lecturer, Bozena Czerny, a leader, world leader in accretion physics, accretion disks, and AGN. I will read the citation to you. The European Astronomical Society's Lodewijk Woltjer Lecture 2022 is presented by Bozena Czerny for her contributions to our understanding of the physics of accretion disks and the broad line regions in active galactic nuclei, as well as for her application of quasars to constrain the cosmological model at high redshift and open a window on the role of dark energy. Congratulations, Bozena. Please come here for the picture. The floor is yours.
Thank you. Yes, okay. I'm really honored to receive this prize, and I'm grateful to the prize committee to notice my results. But I have to mention Professor Bogdan Paczyński. He's not with us anymore, but without him, I wouldn't be here. And I'm also grateful to all my students and collaborators, because without them, working in science wouldn't be that much fun, for sure. Now I will try to talk to you about accretion, disk quasars, and cosmology. And this is quite a lot of things. So I will talk about everything, but from my own perspective. I cannot do a review of all those three topics extensively. So I will start with accretion disks, and I will start this meandering from late 70s, because then we had a huge progress in understanding of accretion disk. The standard model of Shakura-Sunyaev was formulated. And this model explained everything which happens between the innermost stable circular orbit, which is ISCO, and then the rest of the disk, the outer part. But it did not address the issue what is inside, how the material actually gets into the black hole, and that was related to the problem of inner boundary condition used for classical disks. And then we solved this problem in 1982 with Bogdan Paczyński. You can notice we published a paper. I had a different name by then. And this is my only paper with Paczyński. But nevertheless, I'm very grateful to him, because I learned from him how to do really science. And anyway, he was the only person who believed that I'm not as stupid as I look like. So in order to solve the problem of the flow towards the black hole horizon, we had to modify standard equations of the disk, because you can imagine that the inflow, when viscous torque is not very strong, should proceed with more or less constant angular momentum. So instead of assuming that the angular momentum is everywhere local Keplerian and in a classical disk, we allowed for a general angular momentum. But then to solve the equation, we had to allow for the pressure gradient and velocity term, and in the equation of energy, we also had to include advection term for consistency. And then you easily understand what is actually happening at the innermost stable circular orbit. The material soon after crossing this orbit becomes supersonic and flows almost freely towards the black hole horizon. So if you need some kind of intuition, you can look, for example, at Niagara Fall, and then you can see that slow motion is above the jump, and then everything accelerates, and you have free fall motion below towards, let's say, the black hole horizon. So in such way, we solved the problem of the boundary condition at the ISCO. And we noticed that if the accretion rate is below Eddington luminosity, actually the transition to supersonic flow becomes right after ISCO. Therefore, the classical approach of Shakura-Sunyaev is very good approximation. So you may think that it's then kind of a boring piece of work. However, it progressed or meandered later towards slim disk theory, because then Jean-Pierre Lassota actually noticed that advection term will stabilize the disk. And this was a very important issue in 70s or 80s, because the year Shakura-Sunyaev model was published, 73, it was discovered that when the radiation pressure dominates, then the accretion disk becomes unstable in thermal and viscous timescale, and therefore many people lost interest in accretion disk because they stopped thinking such a thing can exist. On the other hand, the observational evidence was quite nice that disks do exist, and this is an example of our feed to the broadband spectrum, which we did in paper with Martin Elvis, and already there we introduced the corrections to the processes in accretion disk atmosphere, and we included corona to model the soft X-ray excess, and it was much more complicated. XPEC was not yet written at that time. Anyway, returning to slim disk, how this stability works. If you look locally at the given radius, at the structure of the accretion disk, surface density versus adopted accretion rate, you see something like an S-curve here. And the low branch, this is gas pressure domination. Then the middle branch is this unstable branch, radiation pressure dominated. And our slim disk model introduced the upper branch, which is again stable. Therefore, if you select an accretion rate which is at the unstable branch, the disk does not get disrupted, or instead it will perform in a kind of limit cycle behavior or outburst. And later, this kind of models were successfully used to model heartbeat states in galactic binaries. Right now, we are also using this model with Marzena Śniegowska to model changing look AGNs, and in the morning session, Marzena presented this work in more detail. Of course, in our work, we are still interested in long-term evolution of the disk, so we are using alpha viscosity, but basically since 1981, we know that the actual mechanism is magnetorotational instability, and that makes the situation of the existence of radiation pressure instability kind of questionable. I mean, the answer is not quite clear. In some numerical simulations, like those which are shown here, you see that apart from stochastic variability, you see some kind of periods of higher activity, lower activity, like traces of radiation pressure instability. In semi-analytical models, of course, those outbursts are much stronger, and I think it's really up to compare to the data in order to decide how that really works. I have to mention that this radiation pressure instability actually can reveal itself also in a different way, because the disk does not have to be vertically more or less uniform. It can develop vertical stratification. And this was also something which I studied. The disk can get stratified into a cold layer and upper warm layer with temperature of a fraction of kV, or let's say 1 million of kelvins, and optical depths of order of 10. With Agata Różańska, we showed, solving radiative transfer, that this kind of temperature inversion is actually possible when electron scattering dominates in the warm corona. And predictions from such model are also quite promising. On the other hand, it's not yet clear that the disk is absolutely stable. Ask Agata Różańska if you want to know more about that. So I have a short accretion summary and 2 comments. First of all, we introduced this advection term in 1982, but actually advection term appeared for the first time in the context of disks in 1977 by Ihimaru. However, that paper was missed, and only the paper of Narayan and T published later about ADAF solutions advertised the issue. And second comment, already in 1983, I published a paper that if I assume the value of the viscosity parameter higher than 0.02, then I cannot get a standard solution of classical simple Shakura-Sunyaev disks. And maybe this is something which is now revealed when we, not me, but when other people can do magnetorotational instability and full MHD simulations. Nowadays, we divide disks into so-called MET states, which MET stands for magnetically arrested disk, and then sane, and those things are just classical Shakura-Sunyaev, and both states are important for modeling, for example, what we see from Event Horizon Telescope. And then I will move outwards, I mean from the nucleus, because there was something which puzzled me for some time, namely, when people draw the accretion disk, the disk is usually very small, and then farther away there are some clouds which appeared out of nowhere, and it's not quite clear what they are doing there. So some people wrote a few papers on the fact. I also did observational papers that actually, if you look at the data, if you don't have a standard disk, you don't have a broadline region. So broadline region should be related to the existence of the cold disk. But then the next motivation for me to think about the broadline region was the detection in observations a tight relation between the time delay of H-beta line and monochromatic luminosity of the source. I was quite puzzled why it is monochromatic luminosity and not bolometric luminosity, which was usually advertised at the basis of ionization parameter. And then I thought a little how this can work. So if we know from observations that radius is proportional to the square root of the monochromatic luminosity, then we know from Shakura-Sunyaev that monochromatic luminosity depends on the product of the black hole mass and accretion rate. And then the temperature in the disk also depends on the mass and the accretion rate, just on the product, not separately on the mass and accretion rate. So if we use observational value of the proportionality coefficient in the first equation, and then we take coefficients in the remaining two equations just from Shakura-Sunyaev, we can calculate the temperature at H beta onset. And this is what we did with my student, Krzysztof Hryniewicz, and we got 1000 kelvins. That was quite remarkable because 1000 kelvins didn't look like an accidental value of the temperature. This is just more or less dust sublimation temperature. And I stress it's independent on mass or the accretion rate. Just for any source, it's true. So then we inverted the problem and we proposed a new model of the broadline region, which is based on dust driving. The accretion disk is not well illuminated by the central source because it is geometrically quite thin in AGN. Therefore, you meet the quite low temperature, much below the onset of the torus. And therefore, you have dust in the disk atmosphere, and this radiation pressure acting on dust can push the material up. Of course, when the material goes up, then material is irradiated, dust evaporates, material falls back, and we have just a circulation of the material jumping up and down, but then this material irradiated is a perfect candidate for material of the broadline region. And we named our model FRADO for failed radiatively accelerated dusty outflow. And if you have doubts whether the presence of the dust in the atmosphere makes a difference, this is the photo which can motivate you. Yes, it does make a difference. And we know that, of course, from studies of stars, because stellar winds from dusty atmospheres, they carry much more material, although they are much less, they have lower velocity than line-driven winds. So we slowly were progressing on development of this model, first analytically, but recently my student Mohammad Nadav made better numerical computations, how a dusty cloud will move under the effect of radiation pressure, with radiation pressure really calculated by integration over wavelengths, sizes, whatever, with full description. And he noticed that if he assumes moderate black hole mass, low accretion rate, and low metallicity, clouds are really jumping, going up and down, and nothing very special happens. It looks like turbulent disk surface. On the other hand, when he allowed for higher mass, higher accretion rate, and higher metallicity, actually he got a stream of material which is really escaping from the region and not a failed wind. And this stream of material can be calculated. It's quite relatively close to the black hole. Farther away, we still have a failed wind. So this picture looks quite surprisingly like what Martin Elvis proposed in the year 2000 for a quasar structure, this empty hollow outflow. But in our case, we calculate exactly the location of this stream of material, the opening angle, basically everything. And also it looks quite similar to the dust model, which was recently proposed by Sebastian Hennig at the basis of infrared observations. But here there is a difference between our model and his model, because in the case of Sebastian, the outflow starts more or less at 1 parsec, while in our case, this is broadline region, so let's say a small fraction of a parsec. But because we think we understood the radius luminosity relation or time delay luminosity relation, I thought that perhaps it's quite reasonable to use that for cosmology. Of course, using quasars for cosmology is not a new concept. You can see here an abstract from the paper by Lodewijk Woltjer, by the way. And already in 1973, he claimed that some quasars with proper radio properties clearly show a Hubble relation. Of course, I concentrated on time delay methods because this is what I think I understand. But those time delay methods are also divided into 2 parts, and they were proposed earlier. First method proposed already in 1999 by Collier et al. This is just using continuum time delays of the disk, and that in principle allows you to determine the Hubble constant. But somehow the method does not work yet. On the other hand, in 2011, the same year when we wrote our paper about broadline region origin, Watson and independently has proposed that line time delays can be used for cosmology. So next year, we also started to do observational monitoring of selected quasars. We concentrated on intermediate redshift quasars because there were already many determinations for H beta line for low redshift sources, and there was a group of people monitoring carbon-4 already, so high redshift. So we went for intermediate redshift sources with SALT telescope. Of course, those time delays are quite long, so we had to wait also quite long. And so far, we are not yet using our Frado model, because in Frado model, in this dust-driven wind model, the emission region is extended, so it's not easy to identify the mean value of the radius. So for the moment, we are still using quite a phenomenological prescription of this radius luminosity relation. And in our first paper, which we published last year, we used only magnesium-2 time delays, and we selected only high accretion rate sources, because for lower accretion rate sources, we think that the dispersion is too large. We were able to produce this standard cosmological diagram, but as you can see, our solution is not in any tension with standard lambda CDM model, which is marked here as a blue dot. We are slowly progressing in this direction. We increased the collaboration, and that led to combination of reverberation measured quasars with cosmic chronometers and with baryon acoustic oscillations. And so far, we published a few papers on that. 2 papers are published, one is submitted. When we use magnesium-2 time delays, we have now 78 measurements collected mostly from literature. Only a few of those sources are ours. Everything is consistent with chronometers and with BAO, and we see no tension with standard model. We included recently carbon-4 measurements from the literature, and everything is still consistent with standard model. What we see for the first time, it is that including time delays really improves constraints from chronometers and BAO, although those 2 methods give stronger constraints than time delays themselves. There are more measurements from H-beta time delays. However, this sample is really very problematic, and for the moment, we were not able to do any decent cosmology with H-beta sample. Then best fits depend on the cosmological model, but in my opinion, it's purely the problem that we took this sample from many people. Each measurement was done in a different way. We didn't include some corrections, etc., etc. We also try now to make this continuum time delays working, but here I refer you to the poster, and the problem is really very, very difficult. On the other hand, there is a stream of new measurements of the time delay from different groups, and we expect also a lot of data, for example, from Vera Rubin Observatory. I think we will have very good data for a few thousand of sources. So it's really worth trying. So summarizing how this future prospects for AGN science looks like, there is most of all a lot of work, because for inner disk, we still do not fully understand the transition of cold disk to ADAF, inner hot flow, warm coronal, jet launching, generation of large-scale magnetic field, etc., etc. For outer disk, we heard during this conference a lot about different outflows like UFO ball, warm absorber, torus. Torus is also an outflow, and broadline region, and all that should somehow be finally unified, right, with reasonable physics and appropriate range of parameters. And then for cosmology, time delay certainly is worth pursuing, but there are also some other methods based on quasars, and some of them are even more successful, I must say, at this moment, like strong cleansing or UV X-ray index. But finally, with better data, all those measurements should finally tell us whether there is a tension with a cosmological standard model or it's not. But we do progress. Thank you.